Hello Internet, this is JF and this is Introduction to Programming in ATS. This is video 4 and chapter 4, data types. Now data types are interesting because on the one hand, it's a feature that seems like it's very easy to understand and easy to dismiss. Like if you tell somebody about data types or show them data types, they'll be like, okay, I get that. I understand that. That seems sort of useful but not really essential. Like I have structs instead of that, or I use enums and instead of that one instance or that one case. And on the other hand, data types separate good languages from bad languages. So a language with ML-style data types is immediately a good language. Like it has a quality floor, and it's above that floor. It can't be too bad. And languages without these data types, they're just garbage. You should accept that. So if you're not too familiar with them, we'll go through them here. And also, even languages that have them, they're variances in how exactly they're used or how exactly they're expressed. So those details will come out in this chapter. So the first example of one is a data type called indopt. So the type is indopt, and then there are two things there are two constructors that create indopts. So you have indopt none down here that creates just itself, so it's a constant. And you have an indopt sum that you give it an int, and then it creates itself of that int. So you can have as many different indopt sums as there are ints, basically. But you only have one indopt none. And what you can do with data types is create them and then pattern match on them. And that's pretty much it. So that's why the entire rest of the chapter pretty much is talking about patterns. All right. So patterns have, if you have a pattern, you have, let's say val. You can have like a constant. So this is a pattern, and this is just a value. So the value side, and then the pattern side. And then if you have a constant, then it just matches itself. So if you have like a tuple and a constant, then you have to match. In order to match the tuple, you match both of these constants. So both of those have to match. If they don't match, it's either a match failure, like in a case. Like if this were case x of if it didn't match this, then that would just be a match failure and it would move on. Or if it fell through, there would be an error. Like it fell through completely, that would be a runtime error. Okay, and then you have void, so you can match nothing. And I've seen a lot of that. Like so print this macro it prints a bunch of stuff and it returns void, and this is matching void. So say okay, it has to return void. You can also say I don't care. It can return anything at all, and just discard that. And you can also say I do care what it returns. And I want to give what it returns a name. So this is println's return value. And then again, you can match tuples or records. And the thing to point out is that if you have a tuple on the pattern side, then everything within the tuple is also a pattern. So you can have like constants, variable names, underscore to dismiss stuff, and this has to match 42, anything, and then anything more. So, but it has to match at least like 3 components. It's just that the latter 2 components, they can be anything at all. All right, and if you have a constructor like from a data type, so let's create that indopt thing. None, and adopt sum. So if you have that, then you can also pattern match on that. You can have constructors and patterns. And pattern match is non-exhaustive. It gives you a warning because even though it happens to be the case that this is indeed an indopt sum, an indopt none, and it's immediately matched, like it knows that the expression. Right now, all ATS knows about this expression is that it has the type indopt. So it type checked it that far, and it says, okay, this is an indopt, and this is a pattern match that matches an indopt. Well, you have one pattern, you have one constructor here, but there are 2 constructors. So it could possibly, like something that's an inopt and you don't know anything else about it, it could be an inopt sum, not just an inopt none. But in this case, we know that this is fine. So we can say val minus and dismiss that warning. Well, if you wanted to make sure that it would definitely complain about this case, it's now a compile time error. Okay. And if you're wondering, like, well, isn't that dumb that it doesn't know it even though it's right here? Well, that's because we're using not primitive types, but we're using unrefined types. So we can wire this up so that it actually can tell the difference, and you actually could have a plus here, and be like, oh, that's totally fine. So I know that those are exactly the same. Because in that case, it would know not just that this is an inopt, but it would know that it's an inopt of some refinement. All right. So continuing, you can also have an as pattern. So v as inopt none, and then if that's the case, then inopt none should also equal v. So it's complaining about macros here. Val v as inopt none is inopt none. Where would it be complaining? So that's fine, but this breaks. That definitely doesn't like that, and it fails at something that looks like it's like macro expansion failures. It looks like a template error with all these PMV errors or such. Yeah, I'm not actually sure what the problem is there. I did wonder reading this, like, X as pat, is it really that direction? Like, what about inopt none as V? Okay, it doesn't like that either. So the syntactic element at as is needed on line 10. So yeah, you can't here. Let's try doing a case then. Inopt none of. Okay, let's do it like this. So case inopt none of. So we're matching against is the inopt none. So this is a case structure, a case that we're going to see in a moment, but I'm doing it right now. We've also seen this before. So inopt none, if it's inopt none as v, so as v as inopt none, then say we matched. Otherwise, we didn't match. So I'm thinking in this case maybe it's the val syntax that doesn't support as's. Okay, yeah, that makes sense. Like, even though it says this is like pattern matching in general, like, it is definitely weird to have the as syntax in a val like that. So okay, so you can use it in cases, but not like vals. All right, and one point: variables can occur at most once in a pattern. So you can't do what you can do like an Erlang and say, x equals 111, and that's fine because they all equal each other. But if you had like 121, that would be an error because then they're not all the same. That doesn't follow. So this is just bad. All right. So we're still talking about pattern match. So we talked about patterns before, and now we're actually talking about matching. So I've gone ahead and shown some pattern matching with the vowels and the cases, but this is where the book actually talks about it. So in a case where value matches a pattern, a collection of bindings are generated between the variables in the pattern and the components in the value. So if you have val xyz equals 1, 2, 3, then you're generating bindings for x and y and z separately. It explains how pattern matching works. So if it's a constant that matches a constant, then yeah, they have to match, and it doesn't generate any bindings. Likewise, void, wildcard, there are no bindings, obviously. If it's a variable, then yes, and that matches anything, and the binding is the variable has the value of whatever component that is of the value that matches it. It says tuples and records work as you'd expect, and constructors work as you'd expect. So if you have val inopt sum 2 equals sum 42, so that works. And if you do the same thing and say x, then you can now print out the value of x. All right, and if you have an as pattern, then X has the value of whatever matches the pattern, the entire pattern, even if the pattern itself has its own bindings, they get generated. All right, now we have matching clauses and case expressions. So a matching clause is this thing up here. We have a left side and a right side of like a fat arrow, this kind of thing. And we have a sequence of these here. So this is a matching clause, and then you have you have a sequence of matching clauses like this. So you can have as many of them as you want, within reason. Like obviously nothing else would match in this case since I'm matching everything right here. But again, there's a limit, and they're separated by bars. And also, each one of these, the right side of the matching clause is just an expression. So it's not like a sequence. Like in Alchemol, you could say print like this, and then semicolon, and then print some more stuff. And all this stuff would be under this one clause. In ATS, like this line is a separate expression from this whole case expression. So you have one expression and then a second expression. If you want to have multiple expressions on the right hand side, of course you use sequence expressions like parentheses or begin and end kind of stuff. All right, and this is all pretty simple stuff. Now we get to enumerative types. So the simplest use of data types, rather than having like two constructors and having one of them take something, you can just have a sequence of a bunch of constructors that are all take nothing. So null array types here. So the weekday type, we have Monday, Tuesday, Wednesday, okay. So he's using of void to say that these don't take any arguments, but you can just omit that. Like it's clear they don't take any arguments. But one thing to remember is that if you do want to give them arguments, you don't do it like this. Like, oh, well, this is it takes an int, because this is how you would create like a refined type. So this would be like a weekday refined by int is where you'd have something like this. If you're going to give them arguments, it's always of and then your arguments. And this first bar is optional. It's also optional in the case up here. And that's just to make it neat, so it looks like a solid bar, because otherwise it looks like that. It looks weird, and also you have to like manually indent this. So if you're doing what I'm doing with like hard tabs, then you have to have like spaces for indentation as well, which is that's like the worst of worlds, to have spaces and tabs. And also that's partly the Alchemol style guide recommends that. So, but the other thing you could do is if you're going to have like something similar like weekday, or actually I have an example right here. If you have them all in one line, then obviously it just looks weird to have the bar there, so you can omit it there. Right. And one thing he points out is that although these are all constants, like this is just an int in the actual, when we compile to C, like this is just a number. Wednesday and Thursday and Friday and so on. But you shouldn't assume that there's some relationship between them, like Tuesday is Monday plus 1. Now again, you can create a relationship if you refine them by ints, but you've seen that in other videos, and we haven't gotten to it yet. All right, size of function is weekday. So this weekday, and it takes a day, and the type is wday, and that's the type of all these. All these constructors create wdays as the type of them. And returns bool. So let's say and he has the second example of his weekday on the left side of the screen. See, it does the same thing. All right. So Saturday and Sunday are false for his weekday, and then everything else is true. And one thing to point out is that you have two cases that both evaluate to false. So Saturday, if it matches that, it's false. Sunday, if it matches that, it's false. But you can't do this and say, Saturday or Sunday. If either one of those match, then it's false. You can't do that in ATS. And also, you notice that you have parentheses here. So if it were just like a bare Sunday, then it would look like a variable, and this would match anything instead of only the Sunday constructor like you want. So like Sunday, like even though we've omitted it, we have the of void. Well, if you're doing when Sunday appears in a pattern, you have to add this back. That might look a little bit ugly, but like the alternative is there are two alternatives that MLs have gone. So one way, the standard ML way, is don't do anything and just warn you about it. Like Saturday, like this would in ML, this would match. This would be just fine. But let's say you typoed it and you said like Saturday like that. In that case, this would be a variable. So this right here, Saturday, is a variable, and this is a constructor. That's having like a typo like change like the nature of something is like so easily is awkward. And in standard ML, they just rely on you getting a warning about that. Like, oh, the compiler will help you notice that. But I don't like that. The way that Ocaml is gone is that case matters. So I think and I forget actually which way case matters. I think it's uppercase. Constructors have to be uppercase, and anything else like a variable name has to be lowercase. So Saturday, lowercase, that's a variable. Uppercase, that is a constructor. Yeah, that's how it goes. But in ATS, you have just parentheses to mark out what's a constructor. And another thing, like again, like I mentioned other languages because if you're familiar at all with data types, then you're familiar with them from other languages, and there aren't many of them. So in Alkabal, the usual advice for programming for pattern matching is use pattern matching as much as possible because it's actually not just because of this, but one reason to use pattern matching as much as possible is that it's super efficient. And like if you have like a huge case, like it's better than using ifs or anything else, or better than using like you don't even need to use like a hash table or something. Like the case is good enough. In ATS, this is just an if then. So this compiles to test Saturday, then test Sunday, then test anything. So it's just like a sequence of if expressions rather than like a jump table or anything weird like that. On the other hand, I still feel like ATS gets optimized very well, not by ATS itself, but by the target language. Like if you emit C and then give it to GCC, like GCC does amazingly well with ATS code. Like I have another video where I show that like there's an example where ATS produces code that C compiles far better, like significantly better than it compiles like the handwritten C would write. So ATS generates C that C compilers like better than humans do. So that's and that seems like it's not a rare thing. Like I've run into that a lot. Like you do something naturally in ATS and it's blazingly fast. But you can also run into corner cases. So all right, so recursively defined data types. So you have these simple ones where it's just a bunch of constants. And then you have sort of normal ones where you have some of them are constants and some of them take arguments. But then you get into the really interesting stuff where some of the constructors are recursive. So it's a char list. I'm gonna call it list like that. And you have I just say nil and cons. And I'll do it like this. So careless nil or careless cons of, and you have a char, so you have some character like the letter A, and then you have a char list. So this char list is the type. So again, this is the whole type of this thing we're creating right here is char list. That's the name of the type. Then we have two constructors, and one of those constructors, one of the things it can contain is a char list of the thing we're talking about itself. So that means you can have like a careless cons with like A, and then careless cons of B, and then careless nil. Actually, you don't have to have parentheses here. So yeah, and then that'll work because this is a char list, which is what the second argument has to be. This is a char again, and then this, even though this is nil, it's also a char list. All right. Let me give us an example of that. So let's say val hello equals see dynamic identifier W day is unrecognized on line 32. Case day. So not the type, but the variable that I'm making there. And we have dynamic identifier O is unrecognized. Should be a character instead. Alright, so that works. We have a careless length function, but since I created hello, I'm just going to create a careless print function instead. So I can use pattern matching, so okay, CS of, and it can either be nil, and if it's nil, it's not going to do anything, and if it's otherwise, if it's con, so say C of rest. In this case, we'll print it out. That's fine, that's fine. I was like, should I use print char here? But the macro is just fine. And then careless print the rest. There you go. Hello. All right. So he's pointing out that the careless length function is recursive and not tail recursive. So he does another careless length that has a helper function called loop, which is tail recursive. So he just passes loop with the original, so with an accumulator that begins with 0. So it's basically a fold operation. But one of the other thing he mentions is that you should have a naming convention that. And he suggests a naming convention where you're only calling your auxiliary functions loop if they actually are tail recursive. That way, a loop suggests efficiency that's actually there. Okay, and then pattern matches can be non-exhaustive. So I mentioned this earlier with like val inop sum. Like it knows that this has the type of inopt, but doesn't know that it's this specific constructor. So this could match. It thinks that this could match inop nuns as well. So they would say that, well, this pattern match isn't exhaustive. Or down here, if I had if you omitted this Sunday, let's say, let's comment that out. It actually accepts that because this matches everything. Okay, bad example. Let's say over here. Okay, so if we didn't include the nil case. Okay, it says the pattern match is non-exhaustive. It doesn't include nil. There you go. So you have to have nil in the case. So it won't let you. It will let you do this if you have if you match everything, of course. But in general, if you don't have some kind of catch-all case like this, then it'll tell you about any kind of missed. And also, if you don't suppress the warning by saying case minus, then it'll tell you about any kind of missed part of your a missed constructor. So if you don't have every constructor, it'll tell you about that. Which means that if you go and you update your constructors, and you're not going to add another day of the week. But if you had let's say data type payment types, then you have so you have what do you have check. Then you have cash. You probably have event. So cash and then whatever cash amount and check of some check number or other weird types. And then you probably want to have let's say this is that you've got cash and check. And that's all the payment types you accept. And you write a program around that. And then later on, hey, we want to also accept these new things called credit cards. So credit card number, your CSV, or whatever. You can create type defs to name these or otherwise make them distinct. But anyway, if you say you have if you add a credit card type, then suddenly your compiler will tell you about all the places where you're not handling credit cards. So you can go through them and you say, okay, well, this needs to handle a credit card. This also needs to handle a credit card. This also needs to handle a credit card. It's very easy to update your program to handle this new payment type you just added. Whereas without this, like if you use a language like Go, where they have unions, I think they have like discriminated unions that are sort of like this, like sort of like data types, but they don't include the warn you about new stuff feature. It's like, oh, that's Rob Pike doesn't think you need that. I'm just going to refer to what I said at the beginning of the video. And then, of course, if you're using a struct and you have like a constant or something, then obviously, C isn't going to tell you about that either. But this is something that any language with like ML style data types does. They'll warn you about, like, oh, you have, since you only use pattern matching to deal with these, and pattern matching is usually, in some of the cases like this, it's usually exhaustive, then it'll tell you about your new cases and you can go through and update your program very easily. All right, and then he's talking about how you can use plus and minuses. So you can suppress warnings with plus. You can leave the warning there with like val. Like this was not actually a compile error. Like inop sum, if I do it like that, the program still builds, it still runs. It just warns you at compile time, hey, this could be something, but it doesn't actually complain about it. It doesn't actually stop. It doesn't actually make it an error. But I can make it an error with plus or suppress it as I've been doing with minus. You know that minus only suppresses the compile time error or the compile time warning. It doesn't actually suppress errors. So if this were actually an inopt sum, if this were actually like a pattern match failure, then that would be a runtime error. Hold on, how much value it run? Yeah, so I compile it and then I run it here, and then it says, hey, at runtime this pattern match failed. So that's another thing about pattern matches. Pattern matches are also cases in your code. If you do minus, or if you leave it like this, where you can have runtime errors. So like a random case like this right here, this could potentially have a runtime error. If you want to make sure that you don't have any kind of runtime errors, use a plus, and then it'll tell you compile time, and then it won't have the code for the runtime error fault part, so it won't need it. All right, here's another example of getting the last element of a care list. Okay, and the point of this is that in this case, he's not matching. Hold on. The outer expression is not exhaustive, while the inner one is. So the inner care list is matching nil and cons with a. So cons, careless cons, it takes like a care and then also a careless. It takes two arguments. But if you just have like a bare underbar like that, then no matter how many arguments, even if you have no arguments, it'll just discard them. So it's careless cons. I don't care what its arguments are. And careless nil, I do care, and it has to be none. So, but he's saying that the outer case, it's not exhaustive. It doesn't consider the case of a nil. So you can suppress that if you want. All right, he talks about another way to do this. So rather than using like a case within a case, he uses a val for the outer case, a val for the outer part, and then a case for the inner part. This doesn't actually change warning. Like, you still get the warning about it being non-exhaustive, but he goes into say that you can suppress that if you want. One thing, like, you can't just randomly change a case with a val, because cases are expressions and vals are declarations. So in order to do this, he also had to say, you had to add this let here to make the whole thing a let expression with val declarations in it. All right. He's hinting, like I've already hinted several times that with dependent types, like refining stuff by int, then you can add capabilities that aren't here. Okay, now I have an example of binary tree search. I'm not going to go ahead and do this example, but it's something like any kind of, whatever you have data types, whenever you have ML style types, people break out like binary trees and different kind of trees because it's easy. It's very easy to do. Right. Yeah, so this is a function, bstree in ord, that goes through this data. So the data type is you have an empty constructor, then you have a branch constructor that has two trees on either side of it, and then it has a string, so then in the middle. So this is a function that goes through that in order. So it goes to the left side of the branch, then it applies its closure to the middle part of the branch, and then it goes on the right side of the branch. And one thing that jumps at me about this code is not what he's going for, but this syntax right here. So you've got a case expression. You've got a case. You have pattern matching, and then you have just random open brace and a close brace with val declarations between them. So what that looks like to me is a where expression, but it doesn't actually say where anywhere. So hold on. Let's add something. So normally I would do this like nothing where something something. Let's say if we just do the braces by themselves. Okay, pattern mesh is unexhaustive. Line 9. Okay, let's suppress that again. Hello, main world. One other thing to point out, I have this main function at the very top, but it runs at the very end. And that's because all this stuff, all this these val, like all this construction that I'm doing down here, and the side effects that I'm doing down here that are at the top level, they're like just under like val declarations and so on. All those get put into a function that runs before main does. So the main is your program. So in any kind of dynamic file that you load, that you compile into your program, all this kind of top level stuff happens before main. And the other thing to note out is that this is syntax apparently. So there are two terse ways to do stuff in ATS. You can have so let's say some kind of function equals parentheses, and you can have a bunch of sequence expressions. So you can have do A then do B, or you can have some function make it equal, and you can have a bunch of declarations and say okay val XYZ equals 42 or whatever equals something. Val equals something. You can do all this. So you can have a sequence of declarations or a function loop and go on. All right, so you can just bare braces for declarations or bare parentheses for expressions. All right, or it could be very verbose and have like let and a bunch of other stuff. But yeah, this is interesting. I did not know that this was the case until I came upon this example. All right. So this is another example of a binary tree search. It's also an example of guards. So what he was doing here is okay. So case 0 of match everything, and then if the sign is less than 0, do this, or match whatever if the sign is greater than 0, do this. So this is like a sequence of if expressions. The way it's done here, but you can also have this anywhere, of course. So I could say. But that's not gonna work. Let's do this properly. So it matches hello against a variable, so it binds hello to the stir. So stir now means hello, but only where debug, or only when debug. No, so it's not a where expression. That's very different. Okay, and it's hard to notice that now. So line 57. Hello, nothing. Doesn't happen. Oh, this debug is false. Okay, let's make it true. Hello, line 57. Line 57. So yeah, you can use when with stuff like that, where you can have other expressions there, Boolean expressions. Now, it's inserting to a binary tree, and this is all This is something you can open the book and you can go through this if you want, or do any kind of tree stuff you want. It's very easy to work with trees when you have data types. All right, now we have another example, evaluating integer expressions. So this looks pretty noisy. But what this is, you have constants, or you have negation of a constant, or a negation of an integer expression. So it could be a constant, or it could be something more complex. So this is basically like any kind of operations you do with, like, 2 plus 2 times 3, minus 4, minus -4, that kind of stuff. You can encode this expression in this data type, as this data type. So this would be like what is it, IEXP constant 2. You're adding that to IEXP. What is it? Add 2 to IEXP constant 2. This is 2 plus 2 in this data type. So it doesn't look too pretty, but it allows you to build. You can like parse a string and then build this and then evaluate it very easily. Evaluating it is very easy. So even though it looks kind of noisy, obviously you can just you can write an eval function for this and add everything together, and it'll be incredibly easy to do. All right. But the other thing I like to point out here is that this really is noisy. So let's sort of jump ahead and let's do an integer expression, integer exp.stats. So we're making a statics file. Data type IXP equals constant, let's say con. There's another thing I didn't notice before. You don't have to have parentheses if there's only one thing. So yeah, you con of int with parentheses, or just have a bare int. All right, and then we have neg of IXP. Why does it use parentheses and around? Maybe I'm assuming it doesn't actually matter. That's just style. Okay, so sub mul div. So we have we have constants. We have negation, addition, subtraction, multiplication, division, and we're putting all this in a stats file by itself. Now you might not want to have like the reason to have it like named like this is that if you have like two data types with its shared constructors and you load both of those and there's the same namespace, then the latter one wins. Which means if you're working with the former one, like say I have another data type, it's like blah, and it has div of float. Well, if I'm working with if I'm trying to work with integer expressions, and I have like a mul of like I want to multiply 2 and 5 divided by 3, so I have a div here, and then con 5 and a con 3. So it's 2 times 5 divided by 3, but randomly this div is no longer the div I want. It's the div from blah, and I get a type error, and it's a mess. So you don't want that, and that's why he always names, he sort of does like manual namespacing like that. But that's an option. That's one option. Another option is to use like actual namespacing in the language. Let's say IXP. What do they call it? Integer exp. So I'm statically loading that file I just created that has this data type in it. And now I can say something like, what's it? Just XP equals, let's say that the same one I just did. So 2 times 5 divided by 3. Okay, so that'll be con 2. So it's still a little bit noisy, but I feel like it's easy to deal with because you know that this is just the namespace. You don't have to worry about it. Mul yeah, that works just fine. So that's using the namespace with the mul and the adds together, and I feel this reads a little bit better than just having it having an IXP mul like that as one word. And of course, you could have it something else that's more convenient, or you could even do something like mul con 2 div con5, con3. It's the same thing, where, and then that also works. And that works even if you have some other random like data type blah div of float. Even though you have this here, this div doesn't refer to that. It refers to what it's to where the where expression with the static load of the integer expression that's at. So it refers to the div in this other file, even though there's this right here. So that's another thing you can do. Make it like real nice, but obviously if you have a bunch of these separately, then you might want to do something else. Those are options anyway. Just go and leave this there. Hold on. Let's be clear about what it's complaining about, actually. Mismatch of static types. The actual term is integer expression. The needed term is float type. On line 67. I guess I'm wrong, actually. Seems like it is pulling the div from there. I don't think parentheses are going to actually fix this. Okay, at least that's not the case. At least it's not that it's not actually statically loading once it's already loaded. No, it's still doing that. And since I did comment it out just now, it's still getting it from this file. It's just somehow the div is still messing with it. Local. The actual term is blah, the needed term is integer expression. Okay. All right, so your two realistic alternatives then are use a namespace, or do manual namespacing like he's doing here. So you can't actually do the thing I just said you could do. Sorry about that. It's good that I accidentally tested that, because I wasn't going to test it. I wanted to delete that and just go on. Okay. So this is an example of a really complex integer expression using this data type. Yeah, saying, if you have some string form and you turn that into an abstract syntax tree using this data type, then we're parsing. But we're not going to do that here. What we are going to do is evaluate it. So let's write an evaluator. It's going to return an int. So it's a con of any number, then return the number. It's a negation of any expression, then negate the eval of the expression, of course. And then again, sub int and add. We'll do some copy and pasting here. E1, E2. So you need to evaluate both of these and then add them together. So eval. And obviously, you can use an accumulator as an int, just an int as an accumulator. Actually, I'm not sure that's so obvious. Never mind. I'm talking about doing this tail recursively. It's like, no, this is a tree we're working with. So, all right, and boom. Stack identifier IXP, that's because its actual name it's in that namespace. All right, now let's evaluate that and print it out. And exp equals 2 there. Let's go ahead and silence this main so it doesn't confuse system. It doesn't continue to confuse things. All right, so exp equals 2. So apparently 2 plus 5 divided by 3, 5 divided by 3 gives you 0, and then 2 plus 0 is 2. That's math. All right. So that's an example of like, okay, now that we have integer expressions, let's not just have expressions, but also have like Boolean logic. It does this by having a second data type. He's using the thing to point out here is using and. So these are two data types. They're two separate types, but they're mutually recursive. Like their constructors can contain each other because they're anded together like this. Without the and, then this exp here, this would be unbound. Like, what are you talking about? I don't know what kind of type that is. Right, and again, is using and to have mutually recursive functions. All right, and that is the end of chapter 4.